Okay, for number 3, let's continue and discuss a point here. How many gas molecules are on the left and how many are on the right? There are 2 gas molecules on the left, and 1 plus 1 is 2 gas molecules on the right. So, which side of the reaction fills the space of the container of these gas molecules better? And the answer for this one is, that's a trick question because neither of them does. 2 gas molecules fills the space just as well as 2 gas molecules does, and so neither one is really favored, and that's why I had to go back and fix this answer on the solutions. If you didn't notice that, I went back and fixed it. So what happens to the number of moles of O2 and the number of moles of NO? Well, nothing, because the reaction is not favored left or right by changing the pressure or the volume. 2 moles or molecules of gas fills the space just as well as 2 does, and neither one is favored, and there is no change. How about 4? Decrease in the molarity of SO2. So this went down, and the right side is weaker. What's the effect on the O2? If the right side is weaker, then going to the left is not as strong for a moment. Therefore, going to the right is the strong side, the strong direction for a moment. The equilibrium will shift toward the weakened side. The weakened side. This is decreased. So everything will shift to the right. What will that do to the O2? If we shift it to the right, it will make more O2. If it shifts to the right, how does it do that? It uses up the stuff on the left. Therefore, the SO3 concentration will go down. Decrease in temperature. If you decrease the temperature, you've weakened the left side, and everything, all these equilibrium expressions shift toward the weak side for a moment. So this will shift left. What will the SO2 do? It will go down, because how does it go left? It uses up the stuff on the right. B. What will happen to the SO3? If this is shifting left, well, that means it's making more of the stuff on the left. Well, it's also replacing some of the heat, some of you will notice too, right? We decreased the temperature, we took out some heat, and then it shifts left, and it will try to replace the heat, but also it will be making more of the SO3. So the SO3 concentration will go up. 6, increase in pressure. Okay, so here's a pay attention moment. Increase in pressure. Everything's crammed together more. Which one fits into the crammed together space more? 2 gas molecules or 3 gas molecules? Well, 2 fits into a tighter situation better than 3 does. So if you increase the pressure, this equilibrium will shift toward the side that has fewer gas molecules. So this will shift left. What will that do to the molecules of, or moles of O2? If it's shifting to the left, it will use up the stuff on the right. The O2 will go down. What will happen to the SO3? If it's shifting to the left, it will make more of the stuff on the left. The SO3 will go up. On number 7, on the left side, we have 7 gas molecules. On the right, we have 2 gas molecules. Also, delta H. Let's introduce this. Delta means change in sign, so the change in heat. What happens to the change in heat when this reaction runs? Always assumed to be to the right, by the way. When we talk about it just in general terms, we always mean going to the right. Well, what we're going to do is sort of measure the potential energy. And if we say it had a certain amount of energy on the left and a certain amount of energy in the chemicals on the right, what happened? If this is a negative number, then the energy in the chemicals, inside the chemicals themselves on the right, is less. It went down compared to the energy on the left. The energy inside the chemicals themselves went down as we proceed from left to right. Negative number. It decreased. Where did that go? It came out as heat. That's how I knew to put heat as a product on the right side. Because if the energy came out, that's kilojoules, by the way. That's joule. That is the energy unit. There was a Mr. Joule. So it gets a capital J if you're going to just put one letter because it was a person. So, and kilo means thousand, so when you run this to the right, inside the chemicals there is less energy. There is 6.7 thousand joules less in the chemicals on the right side than there was on the left side. The energy came out. Where did it go? Well, it escaped as heat, light. We usually just write heat. And it was produced. It came out as the reaction ran to the right, so heat is a product. So list every way you could shift this equilibrium to the right. So we could make the left side stronger to make it shift to the right. That would mean we could put in more A, more B, more C. Also, this has 7 gas molecules and this has 2. So if I cram this all together, it'll shift toward the side with fewer gas molecules. So we could increase the pressure and it would shift to the right. What about less? Well, we could do some lesser things. If we wanted to shift to the right, we could reduce the amount of the stuff on the right. So I could reduce the amount of D, reduce the amount of E, and I could reduce the amount of heat. Also, how did I increase the pressure up here? Well, basically, I did it by reducing the volume. If I could squeeze this vessel down to a smaller size, then that would increase the pressure. So increasing the pressure and decreasing the volume are basically the same thing. So I could have a less volume, and that would be the same as decreasing the pressure. And it would drive the reaction to the right. On 7b, list every way you could shift this equilibrium to the left. We basically just reverse everything. If you do the opposite, you will get the opposite effect and everything will shift to the left.